Hello everyone. First of all, let me introduce my name first. My name is Infantri Siahaan and I am from Mechanical Engineering student of Udayana University. And now I want to presenting about modern alloy production. So this is the topic that we will discuss in this presentation. And okay, let me begin. Introduction. The production of modern alloys involves a diverse range of methods, including melting, casting, and fabrication technique. The choice of manufacturing process depends on factors such as the specific alloy system, the desired product form, required condition, and necessary properties for its intended application. Most commercially available alloys today are made using refined melting and solidification techniques, ensuring both quality and cost effectiveness. These production methods encompass traditional air melting, vacuum melting, and powder production techniques, each with its own distinct advantage and limitation, as explored in detail within this chapter. Effects of alloying on solidification. Solidification of alloys is more intricate compared to pure metals due to the presence of multiple elements with varying melting points. While pure metals solidify and melt at specific temperatures, alloys exhibit a range of solidification and melting temperatures. This results in what is known as a mushy zone during alloy solidification under equilibrium condition. The mushy zone represents the temperature range where both solid and liquid phase coexist. The point at which solidification initiates is termed the liquidus temperature, while the temperature at which solidification is finalized is called the solidus temperature. Different alloy compositions exhibit distinct liquidus and solidus temperature, which are depicted on binary phase diagram by liquidus and solidus lines, respectively. The process of solidification commences when some of the liquid metal begins to freeze at the liquidus temperature and continue until solidification is complete at the solidus temperature. Next is solidification structure. During solidification, the solid-liquid interface typically undergoes one of three types of crystal growth: planar, cellular, or dendritic growth. As we can see in here in this picture, this is the A is the plane growth, B is cellular growth or cell growth, and C is dendritic growth. The specific type of growth is influenced by how heat is extracted from the system. Planar growth occurs when there is a positive temperature gradient ahead of the solid-liquid interface, resulting in heat removal through conduction into the growing solid. This creates a smooth interface and planar growth into the liquid. Conversely, if there is a temperature inversion leading to a decrease in temperature ahead of the interface, cellular or dendritic growth occurs. The distinction between cellular and dendritic growth is primarily based on the degree of undercooling. Small undercoolings tend to produce cellular growth, while larger undercooling leads to dendritic growth. In pure metals, undercooling is typically caused by thermal supercooling, whereas in alloys, it can result from a combination of thermal and constitutional supercooling. And we can see here the difference of solidification of metals and solidification of alloys. If we compare with this picture, we can see the cell growth and dendritic growth. We see that solidification of metals result in the formation of cellular growth or long columnar crystal, and the solidification of alloys result in the formation of dendritic growth. We can see solidification of alloys here. It's the same form with dendritic growth, like that. Next is melting furnace. A wide variety of furnace technologies are available for melting metals. In steelmaking, for example, Pig iron is produced in a blast furnace from iron ore, limestone, and coke because it contains excessively high level of silicon, manganese, carbon, and other elements. This liquid iron, together with scrap and fluxing agents, is then introduced into either a basic oxygen furnace or an electric arc furnace for further refining with oxygen. So this is the step by step of how we can get the pure iron from blast furnace. Next, first one is electric arc furnace. One of the furnace most commonly used to melt steel alloys is the electric arc furnace or EAF. A typical EAF is a refractory line vessel with a bowl-shaped heart that is covered with a retractable hemispherical roof. A modern mid-sized steelmaking EAF can produce a quantity of approximately 80 metric tons of liquid steel in a time span of roughly 1 hour. Second is induction furnace. Induction furnace have become a widely used means for melting ferrous alloys and increasingly non-ferrous alloys as well. The key to the ready acceptance of induction furnace has been the excellent metallurgical control that can be exercised, coupled with relatively low pollution compared to copper furnace and good thermal efficiency compared to EAF melting. Induction furnaces are very efficient, are made in many different sizes, and are relatively simple in design and operation. Small quantities of materials can be melted rather quickly, which allow metal to be delivered at regular time intervals. A wide range of metals can be melted with this type of furnace, although little refining of the metal is possible. The third is vacuum induction melting furnace. Vacuum induction melting can be used to advantage in many applications, particularly in the case of the complex alloys employed in aerospace engineering. These advantages have had a decisive influence on the rapid increase of metal production by VIM. VIM is vacuum induction melting. Next is remelting. There are two commonly used remelting processes for metal refinement: electroslag remelting or ESR and vacuum arc remelting or VAR. In both processes, an electrode is melted as it advances into the melting region of the furnace. As the working phase of the electrode is heated to the melting point, drops of liquid metal that fall from the electrode phase are collected in a lower crucible and rapidly solidified. The next topic is molten metal processing. Fluxing. Fluxing of molten metal is often the first step in obtaining a clean melt. Fluxing is a term commonly used in foundries and melting departments that refers to molten metal treatments from the addition of reactive chemical compounds or inert gases. The various functions of molten metal fluxing additive, either singly or in combination, include removing inclusion, impurities, or dissolved gases from the melt, preventing excessive formation of solid phase inclusion, preventing and removing oxide buildup on furnace walls, and injecting or distributing alloying constituents. Next is primary production casting. Is static ingot casting. Several ingot casting processes have been designed and developed for downstream manufacturing process. The most common is static ingot casting, where molten metal is poured into a vertical, open-ended mold. The mold is made of metal, usually cast iron, and is tapered along its length so that solidified metal can be easily withdrawn from it. The fundamental requirements that must be satisfied by an ingot are the capacity to withstand subsequent mechanical reduction operation without rupturing or cracking, with the capability to yield a commercially acceptable finished product. Continuous casting process. Continuous casting can take two forms, vertical or horizontal. Horizontal casting is suitable for metals with lower melting points like copper, aluminum, and cast iron. And vertical continuous casting, molten metal is poured into the caster from above. As it travels through the water-cooled mold, its temperature decreases, Solidification begins at the center of the mold and progresses outward, forming a wedge shape as it moves through the solidification and water spray zones. Complete solidification occurs beyond this point. Foundries use various methods to cast parts with complex shapes and interior surface. Molds are made in a variety of ways so that the molten metal poured into the mold cavity results in a part with the shape and dimension of the finished form. The choice of molding method depends on several factors such as part size and shape, quantity, tooling, and the molten metal being poured into the mold. Shape casting methods can be divided into three broad categories, such as casting with expandable molds, such as sand, plaster, ceramic, and graphite molding, and casting with reusable, and casting with with high pressure metal injection of the metal into the mold. Next is non-ferrous casting alloys. In terms of tonnage, cast iron is the most common foundry alloy, constituting approximately 3/4 of the worldwide production of castings. Casting is also important in the production of titanium components and indirectionally solidified and single crystal superalloys for use in the production of high-performance turbine blades. First is aluminum casting alloys. Aluminum casting alloys are the most versatile of all common foundry alloys and generally have the highest castability ratings. As casting materials, aluminum alloys have this favorable characteristic: good fluidity, low liquidus, rapid heat transfer from the molten aluminum to the mold. Hydrogen is the only gas with appreciable solubility in aluminum and its alloys. Many aluminum alloys are relatively free from hot short cracking and tearing tendencies, chemical stability, and good as cast surface finish with lustrous surface that suffer few or no blemishes. Next, copper casting alloys. Copper casting alloys are available as sand, continuous, centrifugal, permanent mold, and some die castings. They are generally similar to their world counterparts but have their own unique composition or property characteristic. Next is magnesium casting alloys. Magnesium casting of all types have found use in many commercial applications, especially where their lightness and rigidity are a major advantage, such for chain, saw bodies, computer components, camera bodies, and certain portable tools and equipment. Next is zinc casting alloys. Die casting is the process most often used for shaping zinc alloys. Sand casting, permanent mold casting, and continuous casting of zinc alloys are also practiced, but account for less than 10% of zinc casting tonnage. All processes are based on the same family of alloys. The next topic is powder metallurgy. One of the more recent metallurgical developments in the manufacture of modern alloys is the development of powder metallurgy processing. Metal powder can be produced using a wide variety of mechanical methods as well as biochemical and electrochemical methods. So you can see in here there are water atomization and gas atomization. Let me see. Water atomization. In terms of tonnage, water atomization is now the preeminent mode of atomization for metal, especially ferrous metal powder. The largest commercial application of water atomization is iron powder for press and sinter application, and approximately 60 to 70% of the world's production of iron powder, which now total more than 600 metric tons per year, is produced by water atomization. So this is the process of water atomization in powder metallurgy. This is melting, atomization, particle solidification, and collection. Okay, next is gas atomization. Gas atomization process generally produce powder particles that differ from those produced by water atomization process in terms of their geometry and surface chemistry. Gas atomized powders are typically more spherical in geometry and possess a lower surface oxygen content than their water atomized counterparts. During the gas atomization process, the liquid metal is disrupted by a high-velocity gas, such as air, nitrogen, argon, or helium, that is directed through a specially shaped nozzle. Gas atomization differs from water atomization in several respects. Rather than being dominated by the pressure of the medium in water atomization, it is found that the gas-to-metal ratio is the dominant factor in controlling powder particle size, with median particle size being related inversely to the square root of the gas-to-metal ratio. Okay, thank you for your attention, and I'm really sorry for my bad presenting in here, and that's what I say. Thank you.